Hello, hello, hello. Good afternoon, Internet. Welcome. Come back. Same math time, same math channel. That's right. Right? Like I definitely need to be using phrases like that, seeing I'm called NL Math Man. Oh, hold on, one quick second again there, Twitch. I just have to activate meat space effects. Hold on. Okay, now we're good. We're good to go. Right? That's the different types of dimensions that we have. Actually, we were talking about dimensions the other day. We've got the virtual dimension, which is our in 2020 the virtual dimension is our real interaction, right? And then we've got the meat space, which is like this needless, I don't know, fleshy prison tacked on to our to our glorious digital, I don't know, interactive world. Anyway, um, a few things to mention today now before we get started. One, you do see my title there probably. This is stream. You can check out my YouTube archive link below. You'll notice that down below the stream here, I do have a link that'll take you directly to a YouTube channel that I have made and populated with all the different videos that I have done. Twitch is really good for saving the videos automatically. Twitch records my past broadcasts just, you know, without me having to do anything, and it saves those for 60 days, which is great. But then past that, I do still want to have the videos available to people, so the YouTube archive will be up in perpetuity, right? That one's just going to stay up. So if you miss a video, well, I mean, if you miss it and it's within the last 60 days, it's going to be here on Twitch. So, you can keep using those. But for all the videos that I've saved, they will be up on YouTube. I have to upload those manually, right? So that'll, maybe it'll be later that evening before the video for that day is up on YouTube. But the channel is there, and it's got all the different videos that I have done for the math tutoring section on here. None of the gaming ones or the other stuff like that, but I haven't done many of those. Those ones have kind of, come and gone, right? Those they're here and then they fade away, right? They're ephemeral. But not the math streams. Those ones are here to stay, right? Because that's what math is about. Math is here to stay. Um, that's a good segue. it's a good segue over to talking about math. But today I'm going to be talking about radicals. You don't see the link? Oh, strange. The link should be right next to where it says About NL Mathman. To the side of that, there should be one that says Miss a Video. Click for my YouTube video archive. Down sort of below the stream on Twitch. Yeah, I'll take a look after the stream and see if there's a different place that I can put the link. But it should be, from what I see anyway, on my Twitch UI, it's directly below the part where it says, my title and all that on the Twitch page. I will send that one out in an email to the class as well for the YouTube archive. But yeah, for now, I'm gonna leave it down there below. So hopefully you can see it. Today, one of the topics I'm going to talk about first is, like it says here, an introduction to radicals. So because I'm talking about radicals, I decided, hey, I'm a literate sort of person who understands words and what they mean. So today now we've got pictures of the most radical of cities, the most radical city in Europe for sure, probably the most radical worldwide, right? Because the most radical in Europe would have to be the most radical in the world. And I don't mean radical in the sense of like, the opposite of moderate or something. I mean radical in like the Ninja Turtle sense, like cowabunga, dude. This town is radical, right? Like, come on. What could be any more radical than this place? And also, I'm on day 42, right? So there's a little bit of a hidden nudge in there, right? 42, 42. I mean, I'd need to do 10 times as many streams before I really got to the reference that I'm going for, but you might be picking up what I'm putting down. Well, let's see. Let's see if anyone in chat can sound off with what place this is represented in my background today. Like I said, the most radical city in Europe, puts it high in the running for most radical worldwide. Let's get another picture. Let's get a different one. Here we go. Yeah. Oh, it looked like that was a shadow behind my head, but it's a shadow on the picture, right? Look at this. This is in the same town. What is this? I've been here 3 times over my nearly 2 years in Europe, right? Yeah, probably my favorite spot in general for vacation destinations, right? Um, yeah, I don't know how many other hints I can give you about this one, other than the water that we're seeing here, the canals. No, it's not Venice, right? We've also got this one. Check this out. Now this is radical. This is like the definition of radical. Whoa! Check this one out, right? Now this is pretty sick. This is this is maybe the coolest bar that I was in the coolest city, right? Like this is a kick-ass spot. This one's called the Flying Dutchman. What this bar was, and it's got nothing to do with SpongeBob, unfortunately. Right? I walk in and I think, hey, there's going to be some SpongeBob references in here. Turns out it was just super cool place with like darts and black lights and various other paraphernalia on the walls. Right? Anyway, I don't see any guesses, and I wanna move on a bit. I want to move on a bit and keep talking about it. So this is, of course, Amsterdam, right? Like I said, the coolest city in the world, obviously. Like what else? Um, yeah, and this is you see in the background here, above the word include or behind the word include, it's a houseboat, right? Very typical little Dutch scene, all right? Houseboats, I didn't know before I saw them, but like houseboats oftentimes are floating on like a block of hollow concrete. It's not really a boat, oftentimes per se, like a boat with like a hull and a gunnel and stuff that can sort of move through the water. It's kind of just a floating block that a home is built on top of. Well, I guess that makes sense, right? It's a really beautiful city for just like if you look at it on a map, honestly, it's one of my favorite places for this because the map of Amsterdam really shows a lot of information about how old the city is because it's like a concentric canals, right? So Amsterdam is kind of like there's like Schiphol, I think no Schiphol the airport. Um, I can't remember now. The main like train station in downtown Amsterdam is like sort of in the middle of this U-shaped canal sort of area, and then the canals just sort of radiate out from that when like a U shape, and another one a bit bigger, another one a bit bigger, another one a bit bigger, and like it's you can see from that sort of how the city grew, right? Because at the center it's the oldest part of the city, and then as it went out, more and more canals were built, right? And there's more and more bridges, and it's got this sort of radiating, almost concentric look to it. It's really cool. And just from a map, you can kind of see that, right? Whereas you look at a city like London on a map, or look at a place like St. John's. St. John's is actually pretty similar to London for the way it's laid out, which is to say, like haphazardly and without any sort of planning whatsoever, right? It doesn't have the sort of clear historical artistry that a city like Amsterdam has when you look at the map, right? Like there's a story that when London had one of its great fires and it burned down. City planner had this idea that maybe we can make it into a grid afterwards instead of having all these haphazard different roads that are going everywhere. And Londoners were like, nope, no, we ain't doing that. We're gonna put it back exactly the way it was before, right? Which I do kind of admire. And that's another piece of Newfoundland history that I guess I could bring up. I would like to. I do like to talk about Newfoundland history a fair bit, but there were actually two great fires in St. John's, so we're obviously ahead of London on that, right? We got a second one in, but when St. John's burned to the ground several times, they did the same thing as in London. They just rebuilt the place exactly, the roads in the same spot, all the little like downtown little like nooks and crannies and twists and turns. I mean, you've seen it if you've driven through downtown St. John's. Like a rat maze nightmare sometimes. It's a better place to walk than it is to drive, perhaps. But yeah, they rebuilt St. John's in exactly the same place as well, same sort of thing as they did in London. So those are cities that don't necessarily have the same sort of organic, you know, history that's shown through the pattern of the roads, right? And also, St. John's city planner. The St. John's city planner was like an ox cart, basically, right? Because it wasn't actually planned. It's a really interesting city for that. In that there was actually British actually forbade local governance in St. John's for like the first like almost 300 years that the area was inhabited. So because of that, the settlement. So people started settling there anyway, right? I've gotten off onto a totally different topic now about St. John's history, but people started settling anyway, even though there wasn't like a central government to like organize things, right? The governor was the fleet governor of the British fishing fleet was the de facto governor of St. John's. the settlement that was there. But of course, that was seasonal. The fleet commander's presence was seasonal, so they would leave, and they wouldn't really sort of govern where people could build or not build. They were supposed to prevent all building there, right? Because the idea was that they wanted to prevent Newfoundland from becoming its own colony, which would then assert its own rights over the fishing ground. They would rather Newfoundland remain a seasonal harbor that didn't have a local population and therefore wouldn't be able to lay claim to the fishing grounds, right? But what ended up happening is the people that did settle there, the roads were just not planned whatsoever. They were just totally haphazard. Whatever sort of path was easiest for the ox cart to take, that was the new road. And that's why downtown St. John's is such like an absolute clusterfuck. Pardon my French. Cluster tabernacle. Yeah, but it's, you've seen the way the roads are. Anyway, boy, got off onto a real tangent there, but that's the kind of thing that if I was a high school teacher right now, this would be the real stuff, right, for the students. They'd be like, yes, we see what to get Sir to talk about in order to miss most of class time. Just get him off to talking about like why St. John's roads are so crazy, and he'll spend like 15 minutes on it. It's great. Anyway, I'm gonna do some math eventually. I'm gonna do some math now. So let's start talking about radicals, like I was mentioning. Back over here. So this is the first unit, Betty Ann, of the next math course that you're doing, and it is indeed on radicals. Um, radicals. I mean, it has a great name, right? Like, come on, anyone who's watched Ninja Turtles would appreciate the name radicals. Um, really, it's not all that difficult. It's actually kind of like fractions. Radicals are just, well, they are just fractions, really. They're just fractions, but in the exponent, right? Now, one reason I want to go down through this a bit is because your guide doesn't actually show radicals the way I feel is easiest, and the way I learned them in university was to think of a radical as a fractional exponent, right? Um, at first, it might seem like needless complication, but I think later on, you'll start seeing that treating them as a fractional exponent actually saves you a ton of work and makes stuff quite a lot easier, right? But so this is going to be Math 2101B, Unit 1, that's radicals. Okay. So, okay. So radical is a root. So it can be square root, which we use as this check marky sign, a cube root, which is the check marky sign with a 3 in there, a fourth root, and then after square and cube, we just call them fourth root, fifth root, sixth root, so on, right? Because once we get to the fourth root, they stop having sort of a real world analog, right? Because again, this talk of dimensions just keeps coming back up. We have 3 spatial dimensions. So cube root, you can see that as being as relating to a cube, of course, right? Because if you have a cube that's 3 blocks sort of in each direction, or that's 3 inches in each direction, say, then it's going to be 3 cubed, or 27 inches cubed in volume. And by the same token, if you take something that's 27, you take the cube root of it, you get 3, right? But we can write. Okay, so we can write radicals as fractional exponents. Now this is where what I teach differs a little bit from what the course teaches, but I do think that it makes things quite a bit easier as it goes along, right? So if we had, say, square root of x, that's the same as x to the power of a half, like so, right? Or cube root of x is x to the power of a third. I mean, you see where I'm going with this probably. Fourth root of x is x to the power of 1 over 4, right? And this now makes it a lot clearer, I think, why some of these things that we're going to see later on work. Because, for example, later on, you might see the fact that, say, for example, a fourth root of x squared is equal to the cube root of x, or square root of x, right? So written out like this, it looks a little bit weird, right? Like, do I just have to remember this? Do I have to memorize it? Why, how do I know that this is true? And what other cases are there like that? But it's a lot easier to know if we treat the radical as an exponent, right? Because if instead of x to the fourth root, we did x to the power of 1 over 4 and raise that to the power of 2, well, we know that if we're raising from the rules that you did before, I believe in one of your previous courses, you know that if we get an exponent and raise it to the power of another exponent, what that means is we just multiply the exponents together, right? So that's the same as x to the 2 over 4, right? Because a quarter times 2 is 2 over 4, right? We just multiply the exponents, which is, of course, x to the 1 over 2 when you simplify it, which is just square root of x, right? So you will see this isn't what it gets into right away. I'm getting a little bit ahead of what the guide is doing, but if we think about them in these terms, it can make some of the math we have to do later quite a bit easier, right? So then I'm going to do a few of these examples here, write as a mixed radical. So example 1, we have root 98. Now, another thing about radicals, like I was saying, is we treat them kind of like fractions, in a sense, right? But what we have to do here now is we have to start factoring out the largest square that we can, right? To simplify, so I'm going to write this down here now. So to simplify, a square root radical, we factor out the largest perfect squares that we can. Because the factoring is going to be a little bit different depending on if we're doing a square or if we're doing a cubed or so on, right? So if we're doing a square, we know that our square roots, like it shows over here, right? Over here, here we go, my cursor's there now. We know that our perfect squares, 1, 4, 9, 16, 25, 36, 49, and so on. Perfect cubes, 1, 8, 27, 64, 125. You will be expected to know all the perfect squares up to, I mean, I would say up to 12 squared, but definitely up to 10 squared. The perfect cubes, you'll be expected to memorize the first 5, and then, of course, 10 cubed. But I mean, 10 cubed is you're just adding more zeros to 10, right? 10's easy. You needn't memorize, I don't think you need to memorize these ones here, but either way, the fact of the matter is when you're on a test, I mean, you got a calculator, right? You want to check and see, oh my God, I forgot what 7 cubed is. Well, guess what? I'm just going to type it in here and, oh, there we go, right? Got them, you know. So you'll have a calculator on any sort of test that you're doing in these, and then obviously in an assignment, you can just Google it or still use the calculator, right? So you don't really need to memorize these ones, is my point. But now if we have 98, we know that we can write 98 as 49 times 2, right? So that's what this one is showing over here in the example. Why is it useful to break it down into 49 and 2? Well, the reason it's useful to break it down into 49 is because 49 is a perfect square, right? We can take the square root of 49 exactly, but we can't take the square root of 98 exactly. If we take the square root of 49, we know that's 7, and then we're left now with 7 root 2. Because what we've done is right. So we factored out 49 because it's the largest perfect square that we can factor out of 98. right? They go on. Let's see here. Where do they do? They do any more? Do they do any examples of cubes here? No, they don't get onto cubes for a little while yet. Okay, okay. I'll try not to get too far ahead of what the course is doing. Um, but cubed is not that much different. You're factoring out cube numbers instead, right? Like that's not hard. Say we had, well, I don't know, say we had like cube root of, shit, I don't know, 375, right? Just for sake of argument. We can call that the same as the cube root of 125 times 3, because 375 is the same as 125 times 3. And we can see up above here that cube root of 125 is 5. So that's going to be 5 times cube root of 3. Or, like I was saying above, we can write this as 5 times 3 to the power of a third. I am totally fine with you leaving it like this if you want. Just I do think that it is important to learn this notation because it will be very useful later on. Right? Let's also look at example 2a here. Right? So now in example 2a, what are they doing? We're going the opposite direction now for simplifying. Or we're expressing as an entire radical rather, not simplifying. So what this one is it's 5 root 6, right? And then we had to express it as an entire radical. So now, I think, personally, I find it's easier to write this one as 5 times 6 to the half, right? Because we know at any point where we're putting something inside of a bracket like this, we always had to do the opposite of whatever operation is there in order to get it in there, right? What does that mean? Well, if we were to write the 5 inside the bracket, whatever we write inside the bracket to the power of the half has to go back to making 5, right? So that's why, uh, well, actually, I'll just put this in a bracket here, right? So we don't really need to concern ourselves with that right now, right? But so what they do here is they do root of 5 squared times 6. The reason you had to put 5 squared, well, like I would show down here, right? It would be 5 times 6, 5 squared times 6 to the half, right? Because 5 squared is what would have to go in there. But the reason it's 5 squared is that if we take this number and now take the square root of it, we get back to this 5 that was on the outside. So whenever we put something inside, if we're putting it inside a square root, we got to square it. Putting it inside a cube root, we got to cube it, and so on, right? But now it's going to be the root of 25 times 6, which we know is going to be root of 150. Right? So instead of just working down through the examples that are already done for you here, I'm going to take the opportunity and do a few examples from the notes questions. So let's see, page 182. Here we go. This is it. I'll zoom in a little. So I'm not going to do every single one of these. I'm just going to pick a few and go down and do those. True or false? Explain why. Well, the principal square root of 25 is negative 5. Well, no, it's not. Negative 5 is a square root of 25, as your notes talk about, but the principal square root is the positive square root. It's just a little bit of terminology to help out there. Match each radical on the left with its equivalent value on the right. It's a bit of an odd one. Yeah. Actually, let's do the practicing ones instead of the check your understanding ones. These practicing ones are a bit more straightforward and a bit more like the ones that you're going to see when you're doing them on assignments or tests or anything. So for question 4a, we're going to be, so this is root 72, right? Now, what's the biggest perfect square that we can get out of 72? Well, I'm going to write out some of my perfect squares over here, right? So 1 squared equals 1, 2 squared equals 4, 3 squared equals 9, 5 squared equals 25. 6 squared equals 36. So this is just an example of a few of them, right? 9 squared equals 81. 10 squared equals 100. That should be enough to write out over here. But we see that, so 72, what's the biggest of these ones that we can factor out of that? Well, obviously, 64 and 49 we can't do, because those are more than half of it, right? So the most you can do is either divide it by 1 or divide it by 2. That's as big as it's going to get, right? So we can't do those. 36, does that work? Yeah, it does. So this is 2 times 36. So this is the same as root 36 times 2. And we know that the square root of 36 is 6, like it says over here. So now I can go ahead and call this 6 root 2. Right? That's all you got to do for those ones. Um, mm-hmm. Is there a trickier one? Yeah, let's do C, because C brings in the cube root, right? So now I'm going to write out some perfect cubes. 1 cubed is still 1. 2 cubed is 8. 3 cubed, 27. 4 cubed, 64. 5 cubed, 125. 6 cubed. Like I said, see, I didn't actually memorize these ones either, right? So let's go back. 216. I really should. I really should know these. 7 cubed is equal to 343. 8 cubed, I do know that one. 512 because of binary. 9 cubed is 729. And then all the 10s are easy, like I said, right? 1,000. So there we go. So we've got a few of those ones written out. We pop back over to the questions that we're doing, right? And I'll actually, for sake of my color coding, let's do this one in black, because black is the color that I did the perfect cubes over here. All right, so we're doing the cube root of 40. Well, what are these numbers? Any of these numbers we can factor out of 40? Well, how can we tell at a glance, right? Well, any of them, is 40 there exactly? Well, no, it's not, right? So the next biggest number we could possibly factor out is 20, right? And 20 is not there either. So the biggest of these that we could even possibly factor out is going to be 8. And of course, we know we can. We can indeed factor 8 out of it, right? So we can call this the cube root of 8 times 5, which is going to be 2 times cube root of 5, right? Again, or we can call that 2 as 5 to the third, right? Now again, I know I'm going to keep saying this over and over, but it seems like an extra step now to switch it to this form. You can just leave it alone. You don't have to, but this is going to serve you well later on. Next one, express each radical as a mixed radical in simplest form. It keeps doing the same ones. Okay, sure. So let's do express each radicand as a product of primes with the greatest possible exponent. Okay, excellent, excellent. Product of primes. Are you asked to do that question? You are. 182 to 183. 182 to 183, and they haven't shown you how to do it really. Oh, okay. And you are asked to do number 6, right? Or am I skipping that? Oh, you're not. They don't ask you to do number 6 yet. Okay. Tell you what, I'll do that one just to get you started, and then I think that's probably we can probably move on from the radicals bit here to start off. But I am going to show you a few of these different ones. Your notes do indeed go into these; they just don't go into them right away, right? So for question 6 here, um, Okay, so product of primes means a factor prime number is out of the radicand until you can't anymore, right? What does that mean? Let's list out some prime numbers. What are the prime numbers that we're going to be working with? Well, there's infinitely many prime numbers, right? So I'm obviously not going to list out all of them, although there are infinitely many perfect squares and perfect cubes too, so that didn't stop me there. It's not going to stop me here. 2 is the lowest prime number. 1, for a definition, just because of the definition, 1 is not a prime number. The definition of a prime number is any number that can only be divided evenly by itself and 1 just isn't a prime number because it is 1. Yes. 2 is extremely important here. 2 is the one that we're going to be using the most. And why 2? Well, because 2 is the only even prime number. But that means every time we see an even number in our product of primes questions, we know we can factor a 2 out. 3 is going to be another common one. 5, 7, 11, 13, 17, 19, 23, and so on. Right? You don't really need to worry about honestly, like by the time we get up to 17, you're rarely going to see that. Sometimes you will, right? Sometimes they'll give you one intentionally. It'll be like 1700 or something, and obviously 17 will come out of that. But most of the time, the ones you're going to be checking are these guys. 2, 3, 5, and 7, and 11 are going to be a lot of the ones you're doing. But just the nature of the way prime numbers work, there are numbers out there that are, factors of primes that are, 7, 8, 9 digits long. We're not gonna deal with that here. But if we had a question like, say, product of primes with the greatest possible exponents. These ones are actually relatively tricky. They are. But let's do root of 3888, like so, right? What can we factor that number into? Well, we know that it can be divided by 2, right? So I'm going to go ahead and divide it by 2. And this is the same as 1944 times 2, right? And generally the way we represent it is like this. It sort of goes down like that, right? And 1944, well, that's an even number as well. I can divide that one by 2. So now this is going to be 972 times 2, and this times 2 carries on like that. We can keep going down and keep factoring out more and more of these prime numbers, right? And 2, like I say, is the easiest one because every time we get an even number, we know we can divide by 2. Now this is a bit painstaking, but I do want to show you that um, we can just factor out 2's until we get to the point where we have an odd number and therefore we have to try something different. Sometimes it takes a bit longer to do it this way, but you're totally capable of doing it. And to my mind, it makes it easier because it's a bit more regimented, right? Oh, I see an even number. Well, I divide by 2, right? Now, of course, some it will be easier. What do you have written by 6? By 6 of the question? This sentence up here, you mean? It's a product of primes, right? Because in 6 it says express each radicand as a product of primes, right? We see 6 over there on the side. So I've written down that product of primes means to factor prime numbers out of the radicand. The radicand is the number under the radical, until you can't anymore, right? So now we've gotten to the point where we found out that 3888, that one is going to be 243 times 2 times 2 times 2 times 2. Now we might have been able to notice from the start, right, what is 2 to the power of 4, right? 4 2's multiplied together is 16. We might have noticed from the start that 3888 can be divided by 16 right away, and that 16 is the same as 2 to the power of 4, right? There are times when you'll be able to take shortcuts here, but to my, the most regimented way to do it, or the way that's going to work every time, is if the number is even, you divide by 2. Now that we have 243, that's not even. Now we got to start trying our other numbers, right? I'll do 243 divide by 3. Hey, that works. Sorted. All right. So that's 81 times 3, which is times 2 times 2 times 2 and times 2. Now, well, now I could go ahead and divide 81 by 3 again, which I'll get 27. I happen to know, of course, that 81 is 9 squared, and that 9 squared is the same as 3 to the power of 4. But let's do a good faith example and keep working at it the way that I've shown, right? So I know that this is 27 times 3, then still 3 and 2 and 2 and 2 and 2. I could have saved myself a bit of space and called that 2 to the 4. And now 27 is, I know that 27 is the same as 3 cubed, but anyway, um, 27 is going to be, I'm just going to write it out like this. 3 times 3 times 3 times 3 times 3 times 2 times 2 times 2 times 2. Now this is, because this is the first one that I'm showing you, I sort of went through and did all of this stuff out. It looks a bit bonkers at this point, right? But we know that what we can call this is, well, there's 1, 2, 3, 4, 5 threes there, so that's 3 to the 5. And this is 1, 2, 3, 4 twos times 2 to the 4. And that is what we are looking to get as an answer to this question, right? Now I know that dividing by the smallest primes, sometimes it seems a bit overlong, right? Like, couldn't we have divided it by bigger numbers? Couldn't we have divided this by, 2 to the 4 from the start? Well, sure. Like if you look at 3888 like that and say right away, hey, I can divide that by 16, then sure. Yeah, absolutely. Go fill your boots. Go do it, right? Personally, when I see this number, I had no idea that I was going to be able to divide that by, say, 81 or be able to divide it by 243. I didn't know. But I did know from looking at it that I could divide it by 2. So that's what I started with. By the same token, say we've got one like C here, where it's the root of 16,000. Now, I mean, pretty clearly I can factor 16,000 into numbers that aren't just prime numbers, right? Like, obviously, this is 16 times 1,000. Like, it's not hard now, is it? Right? And from these ones now, I can start to factor out some primes, right? And save myself a little bit of work now that I've factored it into these two numbers. Because 16, well, I happen to know that 16 is 2 to the power of 4. But say I didn't know that. Say I knew, but I do know that 16 is 4 times 4. So I know that one, right? And say 1,000, well, I can easily enough call that 100 times 10, right? Why pick 100 times 10? Why not just do 10 to the, I could just call that 10 to the 10 to the 3, but we wanted to do this one as a factor of primes, right? So in the end, we need to get to nothing but prime numbers. So 4 is 2 times 2, right? 2, another 4 is 2 times 2. This 10 over here is 5 times 2, so those are all primes. And this 100 is 10 times 10. Now this is going to be 2 times 5 times 2 times 5. So this is another way that we sometimes write these. And generally what I recommend doing is once you get to a number that's a prime number, give that guy a circle, like so, right? So I've broken this one down sort of in differing paths across. And to be very accurate, I should have a multiply sign between all of my numbers that are on the same line, just to show that I'm still breaking down the same one. But what I've done is I've started factorizing this 16,000, finding with 16 times 1,000, and then I just kept breaking each number down until the point where I got to prime numbers for each one. Now I just count up how many of the numbers I have. I have 1, 2, 3, 4, 5, 6, 7 twos. So that's going to be 2 to the power of 7. And then fives, I have 1, 2, 3 fives times 5 to the power of 3. Right? And that's, my mistake. I forgot in both these cases to do one other step. So this is now the square root of those. And this is still the square root of those, right? Because all I've done now is write the 16,000 as a root. Okay. I've sort of run out of space over here, but I'll do it alongside there. To finish these questions, right, this part slipped my mind. We are going to need to take the square root of as much of these as we can. And here now, we finally got there. We finally got there. This is one of the times when it's a lot easier to write the root as a fractional exponent, right? Because, well, what's the square root of 7? I don't know. What is indeed the square root of 7, right? Or sorry, how do we figure out what's the square root of 2 to the 7 rather? Well, the square root, right, is a power of a half, right? So since it's a power of a half, we know that we can divide um, even numbers by a half by 2 evenly, right? If we have, say, 2 to the 6, if we took a half of that, that'd be 2 to the 3, right? Took the square root of it. So we can think of 2 to the 7 as 2 to the 6 times 2 to the 1, and we can think of 5 to the 3 as 5 to the 2 times 5 to the 1, like so. I'm getting really slanted with my writing here now because of the angle of my seat of my seat versus the angle of my paper. And then we can call that 2 to the 3 times 5 outside of the root of 2 times 5. Right? We can keep breaking it down and call it that. Right? Because we know that when we multiply numbers together, that's the same as adding their exponents, right? So if 2 to the 6 times 2 to the 1 is the same as 2 to the 7, 5 to the 2 times 5 to the 1 is the same as 5 to the 3. And the point here is because this square root divides each of these numbers by 2, I took out even ones because this one can be divided evenly by 2, and this one can be divided evenly by 2. So then we're left with 2 to the 3 times 5 times the root of 2 times 5. And that's now just broken it down into entirely, we broke that root down as much as we can into prime numbers, right? And sort of the same deal over here with this one. And I'll carry this one on in green. 3 to the, we want to get, because we're taking a square root, and a square root is a power of a half, we want to get even numbers for the exponents here as often as we can, right? So that's going to be 3 to the 4 times 3 to the 1 times 2 to the 4. We'll call that to keep as many even numbers as we can. The root of 3 to the 4 is 3 to the 2. The root of 2 to the 4, the square root of 2 to the 4 is 2 to the 2. And then we're just left with root 3. So that shows how we would get to the end of that one. Now, yeah, I have gotten a touch ahead of myself, or ahead of the way that the guide teaches. This actually brings me back to a topic that I was just talking to another student about yesterday. That we can't really follow the textbook directly because the guide sometimes does stuff in different order. You see here, the textbook has these topics right next to each other, but the guide takes a little bit of time before it gets onto it. You will see this kind of stuff, right? And it's just breaking one number down into primes, either by recognizing numbers that we can divide by, or simply doing like we did over here, and in each step, just dividing by the biggest prime number that we can. I could have saved myself a heck of a lot of space over here by, from this step on, calling this 2 to the 2, then this 2 to the 3, then this 2 to the 4. I wouldn't have had so many of these 2's to write out, right? But this is how you do those questions. Okay, boy. There's a lot of talking about that one. Switch on back over here. Calculating pay deductions. I wanted to mention a bit of that. This one is for Renetta. Now, I'm only going to be on this one for a second, Renetta, and I think you'll probably see why. Just because it's... Go back over breaking that last one into the answer. Okay, sure, yep. I'll go down, yeah, I'll bring this one back on screen here, Betty Ann. Let me switch back over. So breaking this last one down, what I did is I factored out, let me switch back over to your course, to the ones from the textbook. I basically just split this number into as many pieces as I can. Then down here is where it got a bit differently. So is that this part what you're talking about, or this one? Actually, I'll tell you what. I'll do another one of these questions here now. I'll just really quickly, I'll go down through 6b, squeeze that one down here in the corner because 6b is not going to be super big, right? 6b is the root of, oh, just the last step. Okay. Um, Actually, I'll tell you what. Yeah, maybe I'll get to it by showing you how this one works, right? Because what we're taking is the root of 10,000, right? 100,000. So I know that this is the same as, um, now I could call this 10 to the power of 6, right? 10 to the power of 5. But in keeping with the way that we've been doing it so far, how about I just factor it? I call that 100 times 1,000, right? We know that 100 is 10 times 10, and 1,000 is 10 times 100, and 100 is 10 times 10. 10 is going to be 5 times 2. This 10 is going to be 5 times 2. This 10 is going to be 5 times 2. And then these ones are also, unsurprisingly, going to be 5 times 2 and 5 times 2, which I could have gotten to quicker, I know. But there's all my prime numbers, right? So this next part that I'm going to show is, I think, the part that you were talking about. So that is the same as the root of, so it's 1, 2, 3, 4, 5, 5 to the 5 times 2 to the 5, right? But once we have this part here, now we can sort of break that one down a bit like I did here and like I did here, right? So the thing is, a square root is the same as power of a half, right? So we could think about this as 5 to the power of 5 over 2 times 2 to the power of 5 over 2. And what's 5 over 2? Well, 5 over 2 is 2 and 1 over 2, right? So if we were to take 5 over 2 and break it down into a mixed number, we can think about it that way, right? So this exponent in the corner, or this fraction in the corner, 5 over 2, well, that's the same as 2 and 1 over 2, right? So that's 5 to the 2 times 5 to the 1 over 2. And the same thing here, 2 to the 2 and 2 to the 1 over 2. Now this is getting a bit crammed over here, but I guess I really should have started another page. But then what we call this now is 5 squared times 2 squared, and we can call that times the root of 5 times 2. Well, okay, I will do it on a different page here to show you basically what's going on. Say that we had a totally different question, right? And whatever we got to in the end, we ended up with root of 3 to the 3 times 5 to the 7 times 2 to the 4, right? Say that's what we were given once we got to the end of our product of primes, right? So here now, we know that the square root so the square root is a power of a half, so we're dividing our exponents by 2 is what's happening, right? So, it's a power of a half, we're multiplying by a half, because when we know from our previous courses, right, one of the rules of exponents is that, actually I'll do that over here on the side, one of the exponent rules, is that x to the power of y raised to the power of z is the same as x to the y times z, right? Kind of the same as x to the y times x to the z is the same as x to the y plus z. Now those rules are not explicitly taught in this chapter because it'll sort of rely on you knowing those from before, but those rules are really important for what we're doing here now, right? So the square root basically is like this first case where the z or the exponent outside, is an exponent of a half, right? Which means basically we're multiplying these numbers in the corner, this 3, this 7, and this 4. Those are being multiplied by a half, which is the same as dividing by 2, right? So, right? So since we need to divide our exponents by 2, easiest thing to do is factor out the largest multiple of 2 from each exponent. Well, what do I mean by that? Well, I'll show you here now. So I'm going to 3 to the 3. What's the largest? Now here the factoring is a little bit different, right? Because it's exponents. But we're saying, well, 3 to the 3 is the same as 3 to the 2 times 3 to the 1, right? And we know that because of this rule over here, that if we have two exponents multiplied together, if they have the same base, we add the exponents, right? So we know that 3 to the power of 3 is the same as 3 to the power of 2 times 3 to the power of 1. Same deal here for these 5s, right? 5 to the 7 is the same as 5 to the 6 times 5 to the 1. And 2 to the 4, well, 4 is already a power of 2, right? So that's why I went ahead and did that. So now we divide the even exponents by 2 and put them outside the root, right? So 3 to the 2 divided by, what's 2 divided by 2 is 1, right? So there's a 3 to the 1 outside, or 3 to the 1 is just 3. 5 to the 6, 6 divided by 2 is, of course, 3. So there's a 5 to the 3 outside. And then 2 to the 4, 4 divided by 2 is 2. So there's going to be a 2 to the 2 outside. And then the rest of them stay under here. So there's a 3 to the 1 that stays under here. And there's a 5 to the 1 that stays under here. So this now, this is our final answer. Now this is our most simplified version of this root as a product of primes, is this one here, right? Now we could go back and multiply. We could call this root 15, right? 3 times 5. And we could call this 4 times 3 times 125, right? So 11 times 100, 12 times 125, whatever, right? We could call it that, but we're leaving it as a product of primes, which means all the numbers here should be prime numbers, and they are. 3 is a prime number, 5 is a prime number, 2 is a prime number, right? So this is the kind of thing that you'll be left with in the end, right? Sort of like what we were left with here and here and here. Okay. Um, yeah, I kind of did one of the a bit more involved topic first, maybe for you there, but I think hopefully this is relatively clear what we're doing, right? But for radicals, you're going to be dealing with perfect squares, perfect cubes, and prime numbers quite a bit. Excuse me. So I did Yeah, Betty Ann, if you've got any more questions about this, please do drop a message in chat, and I will, of course, go back and answer whatever you need. For the intro one, I did want to mention is it calculating pay deductions. Now, this is a real straightforward topic, Renetta. So I don't imagine there's going to be, you know, not to say, oh, well, you should get all these ones right, but I mean, come on now, let's, it's stuff that everybody has seen before. It's still arithmetic. It's still easy enough to get things wrong because we're just doing a lot of number crunching. But the actual sort of theory behind the math is, you know, boy, it's not all that difficult, is it? Let's go to a nice summary scene while we're doing this. So this is going to be math 1102B, unit 1, right? And this is page what? Page 193 in your textbook. And I'm just going to do this question twice, kind of, right? So Darren's annual gross salary is a boat mechanic is about $31,000. Right? And basically, what you're going to be doing for this course is just like what it says on here, right? You're going to be calculating all his deductions, his income tax, provincial tax, CPP, and EI, and then just adding it together, right, to see what his total deductions are. It's even easier than if this was that we do a finance economics course. Actually, that one's under the electives category, but no one ever does that one as an elective. Nobody ever does economics. Yeah, I don't know if myself or Jennifer would be teaching that one, because it's kind of a math course, but it's under the electives, right? And electives are the ones that she's doing, which are do tend to be shorter courses in general, and but that's what electives are, right? Electives tend to be the easier, sort of more fun ones. Although we do have some really good electives actually. Now that I'm thinking about it, right? Like the history course, the 20th century history, that one's good, and world literature is great. Those are some really good courses. Anyway, we do this sort of topic in a bit more detail in the economics um, elective, right? But for here, the what makes this one easier is you're not even asked to go look up the real tax rates, right? I would, if someone was doing economics, I would kind of like to do a lesson online about, how we actually go and find out our actual tax rate. Because a lot of people misunderstand what tax rate actually means, what marginal tax means, especially, right? When people talk about tax brackets and being pushed into a higher tax bracket, sometimes you'll hear people say like asinine things like, "Oh, I don't want to be pushed into a higher tax bracket, or I'm going to end up actually making less money than I would before." No, no, you don't. It's nonsense. When you're in a higher tax bracket, only the income over your previous bracket is what's taxed at the rate of the new bracket, right? So if your tax bracket changes at around, say, earning 40,000, and you earn, say, 44,000, the 40,000 and under is at the previous bracket, and only the $4,000 in excess of the 40,000 is what's taxed at the new rate. It's not every cent you have is taxed at the new rate. No tax system works that way, I don't think. Like in the entire world, and Canada certainly doesn't, right? Or Newfoundland's, or there are taxes mostly. There is a provincial component and a federal component, of course, but both are marginal tax rates, right? So when you hear people talk about like, oh, people earning over whatever, like however many $1 million have like a marginal tax rate of 60% or something, 50%. It's like, yeah, but that's only on the money they're making above and beyond that point. It's not on all the money that they earn. Anyway, I don't have the numbers here right now. And like I said, in the economics course, we do a more sophisticated look at personal finance and taxes. For this course, you're just going to be straight up told. You're just going to be told on the page there in front of you, like over to the right. I can't get stage directions to save my life, I swear to God. Over to the right, right? Those you're just going to be told those. The only thing you have to watch out for is that to a maximum. You see this? See this over here? Nope. You see this to a maximum stuff? You got to pay attention to those guys. That's the tricky bit. The teachers try to sneaky, steal some marks from you. But now to figure out, well, what are Darren's total deductions? Well, all we got to do is federal tax. Well, we're just going to do his income, which is 30,987.00. Going to multiply that guy by 15%, 0.15, and that's going to get 3,987 times 0.15. It's going to owe $4,648.05, right? Provincial tax. Next up. So I'm just going to populate the same entry. That's going to be times 0.77. Oh, don't need two decimals. It's important to, to be figuring out, to be converting from percent to decimals correctly when you're doing this. But, other than that, there's not a whole lot of trickiness about these ones. In this case, we would round to 2386 exactly, because 0.99, right? Obviously, for money, we're going to round to two decimal places, but then this 9 causes this to round up to a 10, which causes this to become a 10, which causes this to become a 6.0, right? So that's what we would do there. So CPP, right, is again going to be his total salary multiplied by 0.0495. Right, and again, remember to round up. That becomes 86 because I'm cutting off a 6, which means this cent rounds up. And yeah, the EI. E-I-E-I-O, right? Old MacDonald got laid off. E-I-E-I-O. And old MacDonald got top stamps. No, 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 yes, no. All right. Some people get top stamps. I wish I wish I knew what that was like. 173 0.0173 equals 536.08. Like so. And now, what are the total deductions? Well, the total, I mean, that's not hard to figure out what we got to do for the total. Now, is it by? We're just going to add these ones together. 4648.05 plus 2386 plus 1533.86 plus 536.08. And like most of the opportunities for making mistakes in these questions, honestly, comes from like number crunching, like punching in the wrong digit at some place or something, some, easy mistakes to make, but you've got like loads of chances to make that mistake, right? I gotta say, in all the math tests that I've done in school and university and stuff, I gotta say, like careless mistakes, like just punching the wrong number in the calculator, probably accounts for a solid like half of the marks that I've lost in total. Want to become famous? No, no, I don't. I never want to be famous, actually. See ya. Being famous would suck, man. Like, ugh, all these people like after you for attention, saying stuff to you, trying to like, oh, I don't know. I would much rather be in obscurity with my, three viewers watching me ramble about mathematics. This is nice. It's cozy. It's cozy, is what I'm saying, right? Fame is not all it's cracked up to be. Maybe I know that from a previous life. I don't know. Anyone a Buddhist in chat? Get at me. Tell me if that is how it works. Do you remember things from previous incarnations? I don't know. Um, B. What is Darren's annual net income? Well, that's not hard. Net income is, well, net is equal to gross minus deductions. Right? That's all it is. Net income is just a fancy way of saying take-home pay, is what we often call it colloquially. Right? And of course, in the real world, in practice, you know, um, it requires, there's a whole bunch of other stuff that gets taken out from your take-home pay, right? Like, nope, nope. Do you mean I don't remember things from previous lives? Dang, that's too bad. Um, right? In the real world, take home pay has a lot of other little nickel and dime things coming out of it, right? You've got your like your medical insurance or your uh, union dues or whatever, like other stuff, right? Whereas here we're just going to be concerned about the big boys, the taxes, CPP, and EI. So net income is going to be for this guy is going to be 3987 subtract 9103.99. So then the net is going to be put that down 21883.01. Right? It's easy. It's easier for me to put it down and read it off my OBS screen than it is for me to read it from there at this angle. Boy, the technology he has to produce this stream is incredible. All these monitors. Darren's paid bi-weekly. What are his net earnings for one paycheck? All right. So another source of common mistakes in a course like this is bi-weekly is 26 times a year, not 24, right? It's not, oh well, a month is about 4 weeks. There's 12 months in a year, so it's 48 weeks in a year. That ain't how it works. That's how it would work if every month was February and it was not a leap year, right? But we know that February is actually the shortest month, right? All the other ones are a bit longer. It's actually bi-weekly is 26 pay periods. Right. So assuming he works for all 26 and isn't a seasonal worker off on EI for 2 months of the year, um, or however many months, uh, paid biweekly with his net earnings for one paycheck. We're just going to take net, divide that by 26, and there we go. So we've got 21883.01 divided by 26 is going to equal 841.65. Right. Not exactly a king's ransom, but I guess he's making do as a boat engine mechanic. Maybe maybe he owns his own business and gets to have an economy of scale going, where he knows that as he increases market share, his effective income will increase because the value of his business is increasing, if even indeed his personal income is not. Hmm. Maybe that's what's going on. I see what Darren's doing. He's playing the long game. Say instead that we had some other person. Say instead we had, I don't know, Eric's salary. Let's say Eric earns, I don't know, 48, let's say 54.5. I don't know. He's starting out on a management and professional scale at a mid-sized employer or something like that. I don't know. Right? Let's just pick one, right? Because there is another example that I want to show here, right? So I'm just making this one up, but federal tax. Now, again, like I said before, right? If this was the real world, I would have to go to the tax scales and actually find out, and he would actually be on two different ones. But again, we're not going to mess with that in this course. So all of the answers that we're doing in this course are going to be inaccurate from what it would be in the real world, right? For these sort of incomes, right? But like I said, we're not dealing with that here. We're just going to go straight ahead and use what's on the page there. All right, so we're just going to do our 54.5 times 0.15, and that's going to equal 81.75. Why am I bothering to make up this one? Well, there is, like I said, there's one more teachable moment about these kind of questions that I haven't got to yet that I do want to discuss. So 54.5 times 0.077 equals 4196.5, and CPP is going to be 45 54500 times 0.0495. That's going to be 2697.75, right? But now, but now what? But now what? Look over on the side over here, right? This is why I wanted to bring this up. This is why I want to show this one. What do we got over here? To a maximum of 2163.15. I know for me to point this out now, it's like, yeah, obviously, you know, the maximum, those words there meant something. They're there for a reason. It's very, very common in these questions for this to be where students lose marks, right? So I just want to prepare you before you start. He's over the max, so the deduction is just going to be 2163.15, right? Because he's over the maximum CPP deduction, so his deduction is actually not going to be the number that we found. It's going to be the maximum from the page. And EI, I mean, if they're over the max on one, stands to reason they're probably going to be over the max on the other, right? So it's going to be 942.85. That one is indeed over max as well. $747.36, right? So then say we had question B, say this guy Eric that I made up, say he had the same questions over there that our friend Darren does on the page to the right. For question B, what are the total deductions? Oh, sorry, I haven't done the total yet. So total deductions are going to be 8175 plus 4196.5 plus 2163.15 plus 747.36. It's going to be $15,282 and one. Oh, that's going to be a period, a decimal, and 1 cent. They're like that, right? So there we go. So now his net income is going to be the 54.5 subtract the 15,282.01. So the net is going to be 54500 subtract the answer 39 to 17.99, right? And then so this is B. And then C, if you had to do biweekly again is divide by 26 because it's 26 biweekly pay periods per year. So that's 39,217.99 divide by 26. That's going to give us 1508.38. And again, right, that's actually not the way we would have to do it in the real world. We would have to go on and check the marginal tax rate, see what bracket Eric is in, or rather, you know, see how much money he's earning in the highest bracket, and then multiply that, and then get the maximum for the previous brackets and take those and add on, right? Which is, if you look at your taxes, like when you actually fill out your taxes, that's what the form is designed to do, right? They make it so you only had to do a multiplication once, but what they have you do is subtract the highest maximum below, like the highest sort of tier that you're past, sort of like they subtract the base of your current tier, and then the amount that you earn over that you multiply by the marginal tax rate of that bracket, right? But anyway, this is not an economics lesson. I don't really need to go into what marginal taxes are, but it's super important to know, right? Now let's flick back over here to the intro. On the intro, I did mention that I was going to do perimeter and area of 2D shapes, but actually we're getting closer to the end of the time that I had for the stream today. And yeah, the student who is about to work on that, um, as far as I know, hasn't gotten to it yet. Because Carly, I haven't heard back about the remainder of your unit one, and this is going to be your unit two. So I might be getting a bit ahead of myself to go ahead and do those for you. So I'm gonna wait on those ones. So perimeter and area of 2D shapes. If you were in chat and wrapped with anticipation about finding out how to find the perimeter and area of 2D shapes, I would be curious as to what sort of a person you are and if you are actually real or just a figment of my imagination. Furthermore, I do also have previous videos that cover this topic, and I mean, just go to like I don't know, go to Wikipedia or Khan Academy or something if you're really that interested. It's not hard. Anyway, my point is that I'm gonna get to the perimeter and area of 2D shapes tomorrow, I think, rather than keep going today because yeah, the student who needs that is not really onto it yet and isn't here watching anyway. Okay. But either way, thanks for being here with me today. Thanks for being here. I'm going to leave you with one last look at StreamStar. Why do I keep leaving StreamStar Student up there? I keep doing that, right? Every time I keep doing that. So it's not like it's difficult. I just got to click one little button and then it goes away, right? Like, come on. Um, yeah, I'm going to leave you with another picture of the Flying Dutchman in Amsterdam, the Netherlands, right? And this is me, maybe showing off another meaning of the NL in NL Mathman, right? Newfoundland, Labrador, and now Netherlands. I've only been there 3 times and only for like probably 2 weeks in total, so hardly a Nederlander, not really. But it's a nice town. I gotta say, it leaves an impression. Amsterdam leaves an impression on you. Let me tell you that much. And I was there around Christmas one year, which I didn't see any pictures of that trip when I was looking through my list there. But my God, like downtown Amsterdam in the center, like around the canals at right at Christmas time with all the markets and lights and stuff, it was gorgeous. What a place. I would like to go back, but you know, right now is not the time. Anyway, thanks for watching today. I hope it's been interesting for you. Uh, yeah, stay safe out there, and I hope to see you again tomorrow.